All right, I want to touch on some stuff having to do with query performance tuning. This is, in fact, our last lecture together in this class. So, there's no homework. Originally, I had hoped to do a homework based on this, but we've gotten to the end of the semester. There will not be a homework on this. So, you want to pay close attention to this lecture because some of the questions on the final are going to come from basically this lecture, but I'm also at the end of this going to review stuff that will be on the final and which things to study. The final is worth less points than the midterm, and it is a take home. I believe it is pick 8 out of 9 questions. This does not mean do 9 of 9 questions and expect me to pick for you. Just pick 8. And they should be short answers. This really should not be something, write one paragraph or a short list explaining each question, a few sentences. And I think, as things have gone through this class, we've done pretty well. This has not been a normal semester. I think that's the understatement of all time. But this class has worked out really well. Much better than my other class, I will tell you right now. A lot of the stuff in there I found out I just could not teach remotely in lectures like this. This one we've managed to get through almost all the material I wanted to get to, except for query performance tuning. Now, there was a couple lectures that we never did in this class, having to do with comparing this to other databases. They were I set those out in my list originally as kind of optional. There was 2 lectures, but we did some other things in the class that I think were really good instead. But query performance tuning. Now, the unique thing about SQL is that it is designed to allow you to specify what results you want to get rather than how to go about getting them. And the query planner takes your SQL specification, whether that's update, delete, select, all of them, and it writes a program for this. Now, the original Postgres query planner wasn't very good, but over the years it has gotten better. There are also custom query planners these days where you can actually have it take this, and instead of being an interpreter, it actually writes a compiled C program and runs a C compiler to generate your queries, which can have some tremendous performance benefits. But generally speaking, the query planner is pretty good. That doesn't mean it's perfect, and you can drastically influence what it does when it generates queries. Now, this is no different than any other performance tuning that you do in a program. I'd tell you in Java, the biggest reason why Java is not as fast as some other languages has to do with the oddest things. Garbage collection is one of them, and that is huge. But also, it's how it allocates memory in little chunks instead of allowing you to allocate it together, and whether or not you have cache misses and cache hits inside the CPU. That's what makes a difference in Java. It's not that the language is inherently slow or bad, and they've gone to lots of work. So, SQL queries sometimes tend to be slow. Now, the reason why it is slow is a lot of things having to do with whenever there's a query and it's going to do things, it's going to build a set of basically nested loops that search down through things. Now, if I've got 2 tables and I'm joining them together, what it's basically going to say is, I'm going to take one of those tables and let's say there's no indexes. I'm going to run through every row in one table and match that up with the rows in the other table. That's kind of a naive thing. That may be slow if they're big tables. If they're really small tables, that may be a perfectly good solution. Now, we can improve the performance of this by taking the first table that it's going to run through and say there's only a few rows having an index, so instead of it searching the entire table to find the rows, it only searches the index, which leads it to a small set of rows, and then it uses that small set of rows with the next table that it's going to join to. Now, the key here to take out of this is whenever I can get my inner loop to do a small amount of work, and the next loop to do a small amount of work, and the next loop after that to do a small amount of work, I have a really efficient query. And my results happen quickly. Now, whether that's taking an index, adding things to your where clause, changing which things happen first, which you can influence in lots of different ways, like using a where clause or using temporary tables or using materialized views. There are lots of choices to play around with. So, by and large, I can't say these are the 5 magic things that you do to improve query performance. What I can say is if you look at the queries and you pick out the slow ones and you go, let's try the following 5 things and let's look at it and let's analyze and get the planner to explain what it's doing for each of them. And I know that these 5 things all produce equal results. That I can pick from those 5 and very quickly say, oh, I see. The number one thing for query performance is I'm going to add indexes. So let's take a look at a query. Now this is in the notes. It's a pretty long query. It's got all sorts of things. It's got 2 different sub-queries. It's got group bys. It's got order bys. This is the kind of a thing that you'd normally see in some kind of an application. Okay? And you can improve the performance with some indexes. Now, indexes are not always good. I'll give you some examples. With that particular query, I can do the sorts faster. Okay, in the particular case that I was working with, it took 43 minutes to 11 minutes to do that by adding a single index. That, if you're building a report that's run once a day, that could be a huge win right there. Sometimes you can't get rid of indexes because they support unique constraints, like primary keys, or they're required for foreign key checks. But you also have to, when you're adding indexes, weigh the cost. You're taking up more storage. Every time you do an insert or an update, they can be slower. And there are some times when an index is really, really not very useful. If an index is indexing things that have lots of nulls in it. Okay? In the latest version of Postgres, we can add to an index where a particular value is not null. But if you are working on version 11 of Postgres, or if you are in Oracle or MySQL, or SQL Server, Microsoft SQL Server, you can't do that. You index all of those things. Now, you can't search the nulls, but it still bigs a big index, and the index can be incredibly efficient. So you've got to weigh the cost sometimes of the queries versus the cost of your inserts and updates. Now, most databases run 90% selects. Now, this can be also dealt with other ways. We talked a little bit about doing your backups with a replicated server where the replicated server gets all the selects. Or the replicated server, gets all the selects, and the primary is only doing the updates. Now, if you can split that with a couple replicated servers, you may not care that some of the selects are slow. What you're trying to optimize is all those inserts and updates on that one critical server that's doing the changes to the data. So this is not a cut and dried thing. This is a thing that as you're working with it, you want to experiment. Now, I'm going to give you some examples. I'm actually going to run some stuff during this lecture. There are things that you also should be aware about queries that, you have to put it in context. A really fast query that you run 1,000,000 times is still probably a slow query. If you can do that same query 5 times, you may be able to have some tremendous benefits in performance. And the only thing I can do is give you an example. I did a project, this is 5 years ago now, for a company in Europe. They had a front page that rendered, and it was really slow. Okay, it turns out that the minimum number of queries to render that page, the way they had built it, was 143 queries. I replaced that with a pair of queries, 2 of them, in stored procedures that returned the data from Postgres. And suddenly, they were like, wow, how did you do that? I didn't tune any of the queries. It was because they just had too many individual queries, and it was actually the network performance that was hurting them. It wasn't the database performance. So by bulking everything together and just having two responses back and forth between the web server and the database, suddenly it was lots faster. It meant what their needs were. Now, one of those things you can do is you can use functions inside a select. And we've talked a little bit about the soundex function before. This is an example of where we take soundex of some value and compare it to somebody's name. A pretty normal kind of search. If you're going to use soundex, there's actually a better version of soundex these days in Postgres. Do Postgres soundex and it'll lead you to the library with the better version. But the soundex here gives us an example. Now, this means that it can't use an index on name because the search is actually on the function soundex of name. Now, one of the ways of dealing with this is we can either create a index on soundex name, which is possible these days, or we can create a materialized view. We did one of those in some of the stuff in class. We messed with materialized views. And now we can create an index on this column, soundex users, and be able to search it with an indexed value. Now, the combination of these things works well. And suddenly, instead of searching every row in the table, which the function would do, and it would run that soundex maybe millions of times, this way it uses an index. And indexes are pretty efficient in Postgres. They're not perfect, just like everything else, but they are very efficient at getting to the exact row of data that you're looking for. So you can turn something that's very slow into something efficient. Now, as soon as you do a materialized view, you've also got to deal with the stuff about refreshing a materialized view so that it's up to date and picking up changes. But you know about triggers, you know about look up how to refresh materialized views, and Postgres is also very good at refreshes on materialized views. So, this is something that you can do. Now, this is the ultimate thing, is that now I have this table that has user soundex, and I can pick it up, and since I can put an index on this name right here, okay, I've stored the results of the function. It only has to be run as many times as there are rows, not every time I do a query. That's a big win. And now I can search on it. So if you have function results that you can get, that you can store in the table, or you build indexes on the functions themselves, depending on how the function works, this can be a really huge thing. Now, this is true of a lot of other things. If you need to look up something and it's upper lowercase, but your search is always going to be lowercase, then you may want to pre-generate that lowercase value in the table and use a trigger so that, yes, every time the main thing gets updated that's upper lowercase, it also updates the lowercase only version that has an index that is what you're searching on. Now, all of this leads to a thing called explain plans. And explain plans are a way for you to poke into what's going on in the database. And if you do a search on Postgres and you put in explain plan and monitoring, there's actually tools that are built into Postgres that you can use if you're administering a database that can capture all of the stuff that you would want to run explain plans on, all of the slow queries. And you look at this maybe once a week, you're looking at it and you go, oh, I see I've got a problem with this query. And then you pull out that query from the data and you say, give me an explain plan. An explain plan like this where you just say explain analyze. Okay? And it gives you a plan that looks like this. I've added some stuff to this plan here. And I've also changed the formatting so it fits on the screen. But the important thing is it tells you what the cost at each step is. It shows you the expected number of rows and how often it goes through loops. It tells you what kind of sort operations it used and how much memory. If you're on a system and the sorts are really large, maybe what you need is more memory. Or maybe what you need to do is figure out how to get those sorts to be smaller. It tells you how many loops there are. Each one of these things is a nested loop. It tells you which conditions it's using inside each loop. It tells you how it's scanning. It does a sequential scan on T1 user. Okay? And it tells you the expected cost of doing this. Now, all of this is the information that the query analyzer uses and has up front. And it has a lot of data that it's trying to take together and homogenize and build into, what is the likely best plan for running this query. Now, this doesn't tell you actually what the query did. Okay, this tells you here's the plan it's going to use if it ran the query. So this is fast. Now, the alternative to that is you do an explain plan analyze. Okay, and here's my little table. I'm doing the same sort of a select, except I'm going to add that word analyze right there. And when I do an analyze, okay, it gives you some extra data, but the difference is it tells you how long its planning time is and how long its actual execution time is. Now, let's think about that. If it's telling you the actual execution time, that means that it actually ran the query. Now, you want to be careful, because if you're using explain analyze on updates or inserts to get that actual execution time, it's actually running the update or the insert or the delete. So you want to take some care. Now, if the database has transactions, you can begin a block, you can do this explain analyze, and then you can do a rollback and get rid of the change you just made, so that you're not actually changing the database and still get a query plan out of it. But this also means, that if you're doing an explain analyze and the query takes a half an hour, guess what? It's going to take a half an hour to do the explain analyze, because it's actually going to run this. You've always got to ask the question, well, if it takes a half an hour to run, okay, does that mean I should or shouldn't run this in the middle of day in production on my production database? Something to think about before you suddenly decide to do an analyze on some stuff. Now, I'm going to do a little bit more extensive example here, and these examples are checked in with the lecture notes. So if you want to go run them, which you might want to do, the code is there to go run them. I just ran them and made a couple little tiny fixes because I've had these for a while. I started out with version 8 of Postgres the first time I ran these, and there's been a couple tiny little changes, but basically they're out there. You can run it. You can go explain, analyze, and run some selects. You can try some stuff with some different data. You could run this sort of thing with data from our database that you've run in your homework for, that kind of stuff. Now, when you run these things, you'll notice that your values, ID equals 55, your analyzes that you get, the query plan execution, has actual values in it. This means that if you're doing this, and I know somebody that got in trouble for this, and they were taking these things and it was on tables that had usernames and passwords, you may not want to expose that information under certain circumstances. So be aware that this has actual data. Okay? And with 55, I really don't care. I'm just doing an example. But, before you turn this loose on the world, you may want to anonymize your results. Now, there is a lot of information in here. And when you get a complicated query, the explain plan can be pages long. And you're going to have to delve into it and ask lots of questions. I can't give you a magic recipe that says this is the best way to do it. I can point out some heuristics. You want the innermost loop to have the least amount of data. Generally speaking, you want to look for anything, if you have very much data, that is a full table scan. Okay, when it does an index condition, that means it's using an index. That's probably a good thing. But if you see something where it's doing a full table scan on lots of rows of data, that's usually a bad thing. Okay, that's kind of like the first thing you look for is, do I have any full table scans? You can have full table scans for a lot of reasons. For instance, I was looking at some code that was generated by Hibernate, this object relational mapping system. And Hibernate had been used to generate the tables. It was also generating the queries. But when it went and did the queries, the where clause was in a different order than the index was in the table. And since they were in different orders of the columns between the two, it was doing a full table scan because the index did not have the right things in it. And the next thing was a sort. And you want the indexes in the order in which you do your order bys so that the sort is cheap because it knows the data comes back pre-sorted because it used the index. So the query planner was missing the index completely because the index wasn't in the right order. This has been like for the past 5 years a known problem with Hibernate, is that it'll create indexes out of order, and I have actually seen that. So you scan through this and you look for how it filters data, where it's filtering it, and what kind of results and costs you get. Postgres has built into it, and you can go and change these parameters, the costs that it uses to do these plans. And it has estimates that it just has built in. You may know that your sequential page cost is different than 1.0. Why is your sequential page cost lower or higher? The 1.0 makes the assumption that you're basically on spinning media as opposed to SSD. Your sequential page cost, if you're running your database all on solid-state storage devices, might be better set at 0.4. And you certainly, in that case, don't have a different random page cost. The random page cost is the same as the sequential page cost at 0.4. The reason why they have a different random page cost is because a sequential page is where the read head is, and it goes right to the next place in there and it can read the next block. Whereas the random cost means that your little arm on the hard drive has got to spin over to a new location. If you're using hard drives and large data, the random page cost is actually probably too low here. My experience is that it's better set to 6 or 7 for random page cost. The cost of getting a particular tuple out of a block, that's one row. Okay. The cost of using an index to get a tuple. It likes to use indexes. So if you don't set the index tuple cost less than the tuple cost, you get, bad results. Now, for most databases these days, this is a settable thing. You can do it in IBM's DB2. You can do it in MySQL. Oracle does not allow you to change what its cost values are. SQL Server, also another very old database, Microsoft SQL Server, does not allow you to tweak how it values the cost in its cost calculation. So when you tweak the costs, you can also change the query plan. But remember, those kind of tweaks are at global level across the entire database. Okay? That's a big change. Another change you can do is you don't have to use standard indexes. You can use bitmap indexes and hash indexes. Now, if I were to switch from a B-tree index that's ordered to something like a hash index, first of all, be aware that before version 12 of Postgres, I probably wouldn't do that switch because if you ever restore your database, you have to recreate the hash indexes. But you may have some really good reasons and go, this is just going to become part of my process, is that if I ever restore from a backup, I drop all the hash indexes and I just rebuild them. Because it'll restore the old hash index, not the hash index with the data that's currently there. But if you're going to do a hash index, you want to go out and look at all the queries that have happened for a long time and say, do any of these have sorts? Because a hash index is not a sorting index. That means that it's going to get the data and have to sort it. And maybe do explain plans on a whole bunch of queries to say, okay, I see that I can use a hash index, and are all of these small enough that the cost of sorting is paid for by the better cost of the index lookup. Hash indexes are really good for equals comparisons and not equals comparisons, but really, really good for equals. Because basically, instead of, it being a tree and saying equals, okay, it's on this branch of the tree, equals, okay, I go down another level, equals, I go down another level. I've done 3 blocks that I fetched off of disk, and finally I get to the data. A hash index, almost all the time, the way they've implemented it is a single block hash lookup, which means I only hit 1 block and then I'm to the data. So that is hash indexes. Heap indexes. Heap indexes are very good for large sorts. And again, this is something that, if I wanted to do this and I was really, at the level of, am I going to use a heap index on this kind of thing? I would want to take my database, my production database, make a copy of it, make the change, and then turn around and on the changed database, be able to run explain plans for a few days. So the human cost of doing this and the hardware cost and the time cost of doing some change like this can be quite high. So the first question is, am I saving 3 seconds, or am I turning something that is critical, that's run millions of times, into something that's faster and actually has benefit? I've got to do the cost analysis on the human terms as well and optimize that cost too. So those are kind of my thoughts on explain plans. And in an advanced class next fall, I'm going to cover probably 20 times this much information on performance tuning. I was hoping to at least get you a little exercise where you actually went and ran a couple of these things. Not a big, let's performance tune this thing, but just run a couple and see them. Now, the last detail I would tell you about this is that in Postgres, okay, it doesn't actually delete data until you do a vacuum operation. It just marks the rows as deleted. So if you delete a lot of data, the data is still there. You just can't access it. It's taking up space. It may be taking up time in your searches because, deleted data has to be skipped over every time it does a search. That can have an effect. And you may want to analyze the tables. There is a command to update the statistics on the tables. And the time when you actually want to analyze tables is if you load a whole bunch of new data. Like, today is the day that I loaded 18 million new rows into this table. It used to have 6 rows, now it's got 18 million. Remember that it's a cost-based planner, and the statistics that it's using to build which thing happens in which order in the queries is based on its understanding of the size of the data. And if you don't reanalyze the data, it still thinks there's 6 rows in it, and it thinks it would be just peachy to do a full table scan on it. So you may want to use the analyze command to go in and analyze the table so you update the statistics inside the planner so that it's got current information on how big things are, what the distribution of values is, what the likelihood of getting a particular thing is. And it keeps track of all those. It keeps statistical and size models. So let's leave off with this and let's go actually poke into the final and talk a little bit about what I'm going to put on the final. It's not actually written, but I have a list now of what's going on the final. And let's I'll touch on that.